I am going to discuss adsorption at subcritical temperatures. Let's begin with carbon dioxide, whose critical temperature is 304 Kelvin. I show here experimental data and the unary isotherms for carbon dioxide in AFI zeolite that consists of one-dimensional channels of 7.4 angstrom. I have three isotherms for IRMOF 1 at temperatures of 195 Kelvin, 208 Kelvin, and 218 Kelvin. And the pink line is the adsorption isotherm for MIL53 at 230 Kelvin. We note that all the isotherms are very steep, and by decreasing the temperature, we note that the isotherms become even more steeper. Same thing holds for methane, whose critical temperature is 191 Kelvin. I show here experimental data on the unary isotherms for methane in AFI zeolite, red circles, copper BTC, gray hexagons, IRMOF 1 at 150 Kelvin and IRMOF 1 at 125 Kelvin. Again, we note that the isotherms are steep, and if the temperature is decreased, the isotherms become even steeper. Argon has a critical temperature of 151, and I show here experimental data on the unary isotherms in MFI zeolite, the pluses, AFI zeolite, red circles, copper BTC, gray hexagons, and COF 102, which are these crosses. The experimental data show that the isotherms are all steep, and the steepness of the isotherm is prominent because the temperatures are below 151 Kelvin, which is the critical temperature. The material I'm presenting today is from my paper from 2010, published in Langmuir. Watch also my video on molecular clustering and steep isotherms on my YouTube channel. I proceed further in examining adsorption of CO2 and CO2 methane mixtures in microporous crystalline materials. Let's look at CO2 isotherms at two different temperatures, and these isotherms are determined from configurational-Bias Monte Carlo simulations. This is an isotherm at 300 Kelvin, the isotherm at 200 Kelvin. We see immediately that the isotherms are steeper. In IRMOF 1, here are the set of isotherms at 200 Kelvin and 300 Kelvin of CO2 in fungicide zeolite, an all-silica zeolite that consists of cages of about 11 angstrom, separated from adjacent cages by windows which are about 7.4 angstrom in size. Again, we note that the lower the temperature is with respect to the critical temperature, the steeper is the isotherm. The critical temperature of CO2 being 301 Kelvin. Here are the CO2 isotherms at 200 Kelvin and 300 Kelvin in AFI zeolite. It consists of one-dimensional channels. Let's analyze these isotherms in somewhat more detail by quantifying the steepness of the isotherms. For the set of CO2 isotherms in IRMOF1, fungicide, and AFI zeolite shown on the previous slide, I determined the inverse thermodynamic factor that is defined as the partial derivative of ln qi, where qi is the loading, divided by the partial of ln fi, where f is the fugacity in the bulk fluid phase. These partial derivatives can be determined by analytic integration of the isotherm fits. The steep isotherms require a dual site Langmuir-Freundlich model for accurate fitting. I plot here the inverse thermodynamic factor as a function of loading. This is the data for IRMOF1. This is the blue line is for 200 Kelvin and the red line is for 300 Kelvin. We note that the inverse thermodynamic factor has values exceeding unity at the lower temperature of 200 Kelvin. The same is true for fungicide zeolite. The blue line is for 200 Kelvin, red line is for 300 Kelvin, and for a range of loadings for CO2 adsorption in fungicide at 200 Kelvin, we note that the inverse thermodynamic factor has values increasing above unity. The same is valid for AFI zeolite. There is a range of loadings for which 1 divided by gamma, which is the inverse thermodynamic factor, has values exceeding unity. Now, I'm going to assert, proof will come later, I'm going to assert that 1 divided by gamma is a proxy for the fractional vacancy, proxy for the fractional pore vacancy. So values of 1 divided by gamma exceeding unity implies fractional vacancies greater than unity. Hard to comprehend, isn't it? So we need to examine this a little bit more closely in order to appreciate what this actually means. And I'm going to prove to you that 1 divided by gamma greater than unity is a indication of molecular clustering. Let's try and understand the physical significance of the inverse thermodynamic factor exceeding unity. In order to do that, I represent the vacant sites within a microporous crystalline adsorbent, such as IRMOF1, fungicide, AFI zeolite, MFI zeolite, by use of a checkerboard. And the checkerboard I show here consists of 64 squares, and each square represents an adsorption site within the pore landscape. And I look at the adsorption of CO2 represented by these red spheres. I have 10 molecules adsorbed. Each molecule of CO2 occupies 1 adsorption site. 10 molecules are adsorbed in a total of 64 available sites within IRMOF1. So the fractional pore occupancy is 10 divided by 64. And in this case, I have 10 unclustered CO2 molecules. Let us postulate that molecular clustering occurs and CO2 dimers are formed, and one dimer occupies the same adsorption site as the monomer. So 10 CO2 molecules occupy only 5 sites because of dimerization due to molecular clustering. So let's do the maths. The number of vacant sites available for further adsorption of molecules is 64 minus 5, which is 59. So I can, in principle, absorb additionally at least 59 molecules that are in these available vacant sites. 59 molecules, if they are all unclustered, this implies that the total adsorption capacity is 59 plus 10 is 69. So essentially what happens is that I'm able to absorb 69 molecules in 64 sites. So the occurrence of cluster formation must be interpreted as an increase in the available vacant sites for further adsorption. And that is why 1 divided by gamma is greater than unity. This implies the phenomena of molecular clustering. And for further explanation, in the context of adsorption of water alcohol mixtures, in which case the clustering occurs due to hydrogen bonding, I refer you to my YouTube presentation on cooperative mixture adsorption. So the message here is that at temperatures lower than the critical temperature, molecular clustering occurs because the isotherms are steeper. Put another way, the steepness of the isotherm is a reflection of molecular clustering, and this allows adsorption capacities to increase compared to the capacity for unclustered molecules. Clustering also implies stronger adsorption strengths. Let's see how that plays out for mixture adsorption equilibrium. In my Langmuir paper in 2010, I present a configurational-bias Monte Carlo simulation data for adsorption of CO2 methane mixture at 200 Kelvin. So there's about 100 Kelvin lower than the critical temperature. So from the foregoing discussions, we expect strong molecular clustering of CO2, but no molecular clustering for methane, because methane has a critical temperature that is lower than 200 Kelvin. The CBMC data for CO2 is shown by the red spheres, and the green squares are the component loadings for methane as a function of the total fugacity in the bulk gas mixture, which consists of a 50-50 CO2 CH4 mixture. The predictions of the IAST are shown by the dashed lines. The IAST overpredicts the methane loading. Another way to explain the deviation from the IAST is to plot the adsorption selectivity as a function of the total fugacity in the bulk fluid mixture. The CBMC data show that the selectivity of CO2 with respect to methane is significantly higher by a factor of about 2 or even more than the predictions of the IAST. What essentially happens is that due to molecular clustering, the CO2 clusters are formed, and the methane experiences a stronger competition with the partner CO2 molecules than anticipated by the IAST. Indeed, the IAST theory development does not cater for molecular clustering, and therefore the IAST fails to provide a quantitative description of mixture adsorption equilibrium. This is reflected in the fact that the activity coefficient of methane is significantly larger than unity, whereas the CO2 has an activity coefficient of unity as shown by the continuous red line. So if we have mixture adsorption below the critical temperature, you should expect deviations from the ideal adsorbed solution theory. Conversely, if the temperature at which the mixture adsorption occurs is greater than or equal to the critical temperature, then we do not expect molecular clustering to occur, and therefore the mixture adsorption equilibrium should be reasonably well described by the IAST. Let's see if that is true. I show here CBMC simulations for 50-50 mixtures of CO2 and methane in IRM of 1 at 300 Kelvin, 50-50 CO2 CH4 mixtures in fungicide, and in AFI zeolite. The CBMC data are shown by the symbols here: red circles for CO2, green squares for CH4. For all three microporous hosts, the IAST estimates shown by the dashed lines are in excellent agreement with the CBMC simulated data on the component loadings in the mixture. So at 300 Kelvin, practically no clustering occurs because the temperatures are above that above the critical temperature for methane, which is 194 Kelvin, and for CO2 Kelvin, the critical temperature is 301 Kelvin, which is practically the same as 300 Kelvin, and therefore next to no molecular clustering occurs. So lower the temperature, steeper the unary isotherms, and the onset of deviations from the ideal adsorbed solution theory should be expected. And that is the message from my presentation today.